All right, so in this chapter, we'll talk about equilibrium and elasticity. Okay. So equilibrium is, let's say when you're standing like this, you're in equilibrium, and we want to know what kind of forces are involved in maintaining your equilibrium. So, so when you're standing now, you don't think about it. That's because your brain is constantly adjusting and making sure you're in equilibrium. When you're first born, you're not able to do that. It takes about 9 months for your brain to learn to balance. So what do you guys do when you're first born? You crawl on all fours. That's a more stable configuration. Okay. It's when you walk, see, you have to do the following. What happened now? I'm standing on one leg. When you stand on one leg, your center of mass has to be above that leg. Now my center of mass is about this leg. Okay, so your brain has got to figure it out and do it all fast. And when you're a toddler, you're not able to do that. Okay, so anyway, we'll talk about that. Elasticity is you've all taken a rubber band and stretched it. When you let go of the force, what happens?
It snaps back.
It comes back. Okay, so that's elastic behavior. And in your body, most material is elastic. So, for instance, the important one of the important ones is when your heart beats, when you pump blood, your blood vessel has to expand. If it doesn't expand enough, then the pressure would rise too much, and the heart would have to work harder to pump blood. Okay, so you have to have enough elasticity, but like a thin balloon, it can't expand too much. That's an aneurysm. If it expanded too much and it burst, that's a problem. Okay, so in fact, what happens is we'll learn in this chapter, your blood vessels expand, but after they've expanded a certain extent, then it becomes harder to expand them. Just like a rubber band. A rubber band, it's easy to stretch it initially, and then after you've stretched it a while, it gets harder to stretch it. Okay? So we'll learn all this stuff in this chapter. Okay, so for instance, here's this lady, she's balanced on her toe. And for her to be balanced on her toe, what needs to be true is her center of mass and center of gravity needs to be right above her footprint. If the center of gravity goes to the right, what happens? She'll tip over to the right. If it goes over to the left, she'll tip over to the left. Okay? So this is not easy to do. Okay? So for her to be able to do it, her brain is constantly balancing that center of gravity right above there. Okay. So what happens if she tilts over slightly, if she bends her head slightly over?
She's going over.
I'm sorry?
She's going over.
She's going over. But her brain is pretty powerful. What she does is she'll stretch this leg outwards and bring it right back. Okay? So you're doing that constantly. This is harder to do. I mean, this even my brain can do. Walking. You know? That's easy to do. You know? So what we'll find is for her to balance, here are the two equations. The sum of the forces acting on her should be 0. Okay? And the sum of the torques acting on her should be 0. Okay, so for instance, this part of her body is trying to topple her this way. This force, if you calculate the torque about this point, and we'll talk about this more in detail, is trying to topple her this way. This part of her body is trying to topple her this way. And when the two balance, that is the sum of the torque is 0, and then she won't topple over. Okay? In fact, these two equations are very important. If you become a civil engineer, you do a whole course of statics just based on these two equations. Okay.
What is that middle letter between the E and the
It's
I?
tau.
Oh, what?
Tau. It's a Greek letter. Yeah. And that's torque. This is just some of the torques. Yeah. All right. Again, you just need to be aware that these equations are there. We won't use them too much. And by the way, you will learn that when you stand on tippy toes, there are parts of your bodies that are bearing 4 times your body weight. So let's say if I stand on tippy toe like that, my tendon, my Achilles tendon, is bearing 4 times, well, the tendon is bearing 3 times your body weight, and there's an ankle bone that's bearing 4 times your body weight. Okay. So we'll see those. Okay, so we'll study conditions necessary for an extended object to be in equilibrium. These are the 2 conditions. So, and balance and locomotion are of critical importance to animals. Bones, muscles, tendons work together to generate forces that produce movement or stillness. Okay. How do we produce forces in our bodies? We talked about this. When your muscles contract, they produce force. Okay. And when the tendons stretch, they're like a rubber band stretched, and they store energy. Okay. Remember when the kangaroo hops very efficiently? Why is that? Because it has large tendons which store a lot of energy. Anybody remember how much energy does the tendon give back?
90%.
Very good, 90%. Okay. All right, so again, here's another example just like this example. Okay, so this part of the bicycle, this weight is trying to topple it over, and there's the pivot point. And so this guy is making sure that his torso is behind the pivot point, and it's counterbalancing this weight. Okay, now you guys can see that this part of his torso is much heavier than this. And so just like in a seesaw, when you have a light person in a seesaw, a heavy person sits close by and a light person sits further out to balance. Okay, so the same thing is happening. The light weight is further out from this pivot point, and the heavy object is closer to the pivot point. Okay. So here are the 2 conditions for equilibrium. What this condition says is the sum of all the forces must be 0 for an extended object to be in equilibrium. Okay. And we're talking static equilibrium, meaning an object is at rest. Okay. And this is the condition, sum of the torques must be equal to 0. And we'll learn more about this stuff. Okay. It's, okay. So for extended objects that are in static equilibrium, these 2 conditions should be true. All materials have some give. What does that mean? So if you stretch a rubber band, it stretches. Okay. If I pull this pen, does it stretch? It does. In the most minute way. All right. And your bones, so when I step on that, did my bones compress?
Yes.
Yes. So you will learn when you go for a run, your femur is, the forces it's experiencing when you put your foot down is about 7 times your body weight. And your bone will compress about 0.5 millimeter. Okay? Yeah.
So in terms of elasticity, we're talking, is it stretch and compression?
Yeah, elasticity, so you can, so now you can't use a rubber band, but you can use a spring. You can compress a spring. So elastic behavior is if it comes back to its original shape. Okay?
Okay.
How many times do you want to be able to run?
As often as I need.
As often as you need to. If your bone didn't compress when you put your foot down, and if it didn't come back to its original shape, then you couldn't run again. Okay? before long you were 5 feet, and then three runs later you'll be 3 feet tall. That's not good. All right, so all materials have some give, and we say that they're elastic if when you remove the stress, if they come back to their original shape. If you pull them, they stretch, if you pull them too hard, at some point they'll also break. So all materials have a limit to the force they can bear. Okay. Now we'll also answer this following question: is silk as strong as steel? You might have heard of this. So here's a spider web. Is this material as strong as steel?
Yes.
Hmm?
Yes, or
Yeah.
stronger.
Yes, so it's about as strong as steel. Okay. We'll also learn the following. Okay, so what is the purpose of this bug?
The spider?
No, what is the purpose of this web?
Oh, to catch food.
To catch food. Okay. So now let me tell you what's going on here. Have you guys jumped on a trampoline? Okay, what does a trampoline do? You jump and it pushes you up. Okay? A trampoline is a good spring. All the energy of compression it gives back. Now imagine a bug coming flying in here and getting caught here. And if this were like a trampoline, and if it throws the bug back, it's not doing its job. Okay? So a trampoline, like the tendon, will give back 90% of its energy. In this case, you don't want it giving back all its energy. It gives back only about 35% of the energy. Okay? The silk gives back only 35% of the energy, and then the bug can get caught. Okay? All right, so all designs, everything, all biomaterials are designed with a good end result in mind. Okay? So we'll investigate forces that require for an animal to maintain balance and the limits of these forces. Okay. So for instance, all biomaterials, they can be broken. So bones break. You guys are all aware of that. Injuries such as ruptured tendons or broken bones can result when the limits are exceeded. Yeah. So all biomaterials are elastic. Okay. They have a limit to the forces they can bear, and you exceed these limits, then you can break these things. Okay. So that's the message. Okay. Biomaterials, even those like bone that we think is hard, are elastic. Okay. Elastic meaning they will deform when you apply a force to them, and when you remove the force, they go back to their original shape. Okay. And you want that happening how long? Your whole life. Okay, so you want a lifetime warranty on all these things. If you get sold a defective part, you got to better complain. Okay. So their springiness allows these materials to store or dissipate energy when needed. Okay, so you saw that in this case, in the web, when the bug came and hit this, okay, you had to dissipate some of that energy. What does that mean? You had to dissipate some of that energy. You couldn't give that energy all back to the bug, because then the bug would spring up.
The web absorbs it. If you watch slow motion, when a bug gets caught in it, you'll see the ripples.
Right. And what happens to that energy? It has to be converted to heat. Okay, that's what dissipation of energy means. Heat is the worst form of energy. If you convert it into heat, it flows in every direction. It won't concentrate it back on the bug and throw the bug up. Okay. So you have to store or dissipate energy when needed. Okay. The elastic properties of bones determine whether they support your weight or whether they'll break upon impact. So, okay, so I jump from 2 feet, my bones compress. I jump from 10 feet, that's too much for them to weigh. Okay, and they'll break. All right, so we'll introduce torques in a second. Okay. So here's a door. This is the top view of a door. There's the hinge. Okay. And here are 4 equal forces. meaning let's say they're each 10 pounds. If you apply this force, again, the door will swing open this way. If you apply this force, the door will swing open this way. This force, it'll swing open that way again. How about this force? If you apply a force like that on the door, will it open the door?
You could compromise the hinge though.
Yeah, it won't open the door though. Okay? So this force has 0 torque. Now this is a 10-pound force, this is a 10-pound force. Which is more effective in opening the door?
About the same.
Okay, it turns out that this is more effective on opening the door. Okay, this guy has a greater torque. The torque will depend on this force times this distance. Okay, since this distance is 3 times greater than this distance, this force will have a 3 times greater torque. And that's why they put all the door handles on the end. Not there, not there. This is where it's most effective, okay, the further out you are. You guys have used wrenches, and wrenches with longer handles let you unscrew a bolt easier, okay, and that's what's going on. So the torque is the force times the moment arm. Okay? So this force is the most effective in opening the door. Okay? So we'll consider extended objects like your arm that can rotate. All right, so so here is you'll learn. Okay, so in this case, you learn that this force is the most effective. The further out you are from the hinge, the more effective you are in rotating an object. This guy is less effective. So let me show you something that you may or may not have thought of. Okay, so here is your arm. You're lifting a weight, okay? And there is the muscle attached to the bone, the tendon there. And when the muscle contracts, you're applying a force there. Okay, so there is the force that is applied to turn your arm and lift that object. And you just learned that the force is close to the hinge. This force is less effective. In fact, to lift a 10-pound object, you have to apply a force almost 100 pounds. Okay.
Closer to,
Right, so if you lift a 10-pound object here, the force that your tendon has to apply is almost 100 pounds. Sounds like a pretty bad design to me. You guys should go return your bodies. So why is that?
Short distance.
Very good. So you will learn that to do work, this is force times distance, okay? And this is output work, okay? The thing is, you apply forces with your muscles, and your muscles can only contract a small distance, okay? So because your muscles can contract a small distance, you're willing to, you had no choice but to apply large forces.
so it's force times distance equals output?
No, this is input work, and that's output work. Okay, whatever you put in is what you get out. Okay, so you are lifting a smaller weight a larger distance by applying a larger force a smaller distance. Okay? It's like 100 times 1 is 100, and 20 times 5 is 100. Okay, 100 times 1 is 100, 20 times 5 is 100. Okay, so you are applying a larger input force over a smaller distance and getting a smaller output force over a larger distance. I'm applying a 100-pound force on my tendon and able to move a 5-pound force, 10-pound force larger distance.
Is that one of the contributing factors to why the legs tend to be a bit stronger, just because the bones are longer?
Okay, I don't understand your question.
Because, okay, so you're saying it takes for, just hinge at the elbow, for a 10-pound, say it's a 10-pound weight of some description, it takes almost 100 pounds at the hinge to move the weight, right?
No, that's the force your muscle is applying. So what the point being made here is you're applying large, very large forces. Your body is applying very large forces to lift small loads.
Okay.
That's just the design.
Okay, so it doesn't matter what body part, we're
Yeah,
just
yeah,
talking
yeah, yeah,
where it
yeah,
hinges.
yeah, yeah. The closer you are to the hinge, the greater the force you have to apply. That's what we said. Yeah. All right. So this force is less effective than this force. Okay. All right. So you saw that shown as the top view in the hinge. This force is the most effective in opening the door. This force has zero torque and won't open the door. This force is less effective. So we'll see what the torque is. The ability of a force to cause a rotation depends on three factors: the magnitude of the force, the distance from the pivot point, this is the pivot point, and the distance from the pivot point, and the angle at which the force is applied. Okay, so it'll depend on all of that. Okay, so torques cause rotation. Okay, so when you apply a force to an object, the force will cause acceleration. It'll change its velocity, and when you apply a torque, so let's say apply a force, the torque will make it rotate. Okay, so again, you don't have to remember these formulas. Forces cause acceleration, that is mass. Torques, this is moment of inertia, that causes angular acceleration, making it rotate. Okay, so it'll make it spin faster. All right, so here's a wrench. There's the pivot point. If you apply a force like this on the wrench, okay, this force can be broken up into this force and a force that is perpendicular to this line. Okay, only this part of the force causes a rotation. This part doesn't cause rotation. Okay, so the effectiveness is, the torque is this component of the force times this distance, r. R is the distance. Okay. Or you can also give the same torque like so. You can draw this line, extend this line, the line of action of the force, and this is called the moment arm. Okay? So the torque can be written in terms of the moment arm times the force, or the component perpendicular times this distance. Okay? So they're both equal. So you can calculate the torque either way. And what happens? The greater the torque, the greater the angular acceleration, meaning the faster it will turn. Okay. So you can go look up your cars and stuff like that, your vehicles. The greater the torque that your engine provides, the greater the acceleration you can have. Okay. All right, so here's an example. All right, so the greater the torque, the greater the angular acceleration. Okay, and you saw that. So in a wheel, if you apply force like this, the torque is force times this distance, r. Okay, r is the distance to the axle. Okay, so now let's see how this matters. Okay, so here are these people playing basketball. Okay, in basketball, what do you need to do? You need to be able to start and stop. You need to stop and then be able to accelerate fast. Okay, so to accelerate fast, you need greater angular acceleration. You need to be able to apply a larger torque. Okay, so here's the wheel, and there's the metal wheel which is what you hold to push on. Okay, so the metal wheel where you're pushing on is at has a greater radius, it has a greater radius, and greater radius, so you can apply a greater torque. And you can accelerate faster. Okay? So for
Why are
the
the athlete's wheels angled like this?
that's so you don't topple over. That's for more stability. That's like this. You're less stable this way, you're more stable this way. You can make sharper turns and not topple over. And you can see this in some of the souped-up cars as well on the road. You'll see the wheels like that. So those kids can go make fast turns by slow guys like me and.
Bless their hearts.
Yeah.
They're no match for a speed bump.
All right. So you see the wheels on that guy is the wheels, the metal wheels where you apply a force is bigger. For these guys, it's smaller. What's going on here? So that's where they're applying the force. Okay, so these guys are racers. These guys are going fast. They're not starting and stopping. Okay. When they're going fast, this wheel is turning fast. Okay. And so in a wheel, the speed at which this thing is going is related to the angular speed. Okay. V, the speed at which that thing is going, this wheel is turning, is equal to R times omega. Okay. Omega is the angular speed. So let's say the wheel is spinning at 10 RPM. Okay. The bigger this is, the faster this point is going. Now your hands has got to keep up. If that guy goes too fast, your hands are not able to keep up, to push. Okay, so they make that small, and so your hands are able to keep up. So that's why there, this is smaller, so just so your hands can keep up. Here, you're starting from rest and you want to apply greater torque. Okay, so the designs are different based on the needs. Okay. So in this case, the racer needs to move continuously at high speed, so his wheels spin much faster. To allow his hands to keep up, his hand rim is much smaller than the chair's wheel. All right, so all these things are designed with very good trying to solve good problems. Okay. Now you guys have all ridden bicycles. When you ride a bicycle, when you're starting the bike, so here's the axle, and if the pedal were here, okay, you apply a force and you can't get it started. If the pedal were here, you can get it started. You apply a force, and this would be the moment arm. Right now, the moment arm is 0. The force is going right through the pivot point. Okay, so the torque is 0, and you can't start the bike. When it's there is the moment arm, and the torque is you can start the bike. But if you have the pedal right there, and this is the easiest location to start the bike at. Okay, that's because the moment arm is the greatest, and the torque is the greatest. Okay, so it's easiest to start the bike at this position. Okay, so it's hard to get going if you try to start your bike with one pedal at its highest point. Okay, that's when R is 0. The moment arm is 0. Okay, so your leg press is almost straight down on the pedal. When the pedal is near the top, the moment arm is tiny. This guy is tiny, and the torque is small. Okay. Sign of a torque. A torque is a vector. A vector has magnitude and direction. Okay. So here's the convention. So here's a wrench, and you're trying to open this bolt. There is the pivot point. Okay. If you apply a force like this on the wrench, the bolt will turn counterclockwise. The wrench and the bolt will turn counterclockwise. Counterclockwise this force will have no effect, okay? This force will have no effect, so these forces will have zero torque. This force will turn the wrench clockwise. So the convention is if a force turns the wrench counterclockwise, that is a positive torque. Okay. If it turns it clockwise, the torque is negative. Negative torque tries to rotate the object clockwise. A positive torque tries to rotate the object counterclockwise. Okay, that's just the convention. Okay, so here's the real rule. So what is the direction of the torque? So in this case, okay, the force is applied at that point. So this is the R vector, and this is the force vector. Okay, so here is so you use the right hand rule. So now I'm going to draw the R vector like that, and here is the force vector. Okay, so if you turn from the R vector to the force vector, if you turn like that, okay, so for instance, so let me show this to you. Okay, so here is the R vector, and here's the force vector. If I turn from R to force vector, which way will the screw move? So let's say if I turn a screw in this direction, which way will the screw move?
Is it your direction or ours?
Well, let's say if this was a screw, and I'm using,
Turning counterclockwise.
I'm turning the screw counterclockwise. Which way will the screw go? Up or down?
Oh, it should go up.
Up. That's the direction of the
Righty,
torque.
tighty, lefty, loosey.
Yeah. All right, so that's the direction of the torque. Okay. If you turn from R to F, the screw would go down, and that's the direction of the torque. Okay. So, but again, so all you have to remember is the torque is a vector. It has direction, and the direction of the torque is perpendicular to the plane containing the R and the force vector. It's either up or down. Okay. So, and one direction is taken positive and the other direction. A torque that tends to rotate the object in a counterclockwise direction is positive, while a torque that tends to rotate the object clockwise is negative. Yeah? When you have several forces acting on an object, so in this bicycle you're pushing down on this pedal, you're pushing down and forward on this down here, the chain is pulling the this sprocket this way, this chain is pulling with a greater tension, and the axle is pushing up on the sprocket like that, or whatever this is called. So each force has a torque, and so this force has a torque tau 1, this force has a torque tau 2. So the net torque on this guy is the sum of all those torques. Okay? And if the total happens to be negative, if the negative, then the object will rotate clockwise. If the total torque is positive, it'll rotate counterclockwise. Okay? So you guys have ridden the bike going forward, and then you've done it backwards as well. Okay? So you have to calculate the total torque. Okay? All right, so here's a gymnast. Okay. Her foot weighs that much, her calves weigh that much, her thighs weigh that much, and so on. All right, this is hard to analyze. What we want to know is where does her weight effectively act? Okay, and that's the center of gravity. Okay, so all those forces, you can think of them as acting as a single point, and that point is called the center of gravity. Okay, so now the torque is her weight times this moment arm. Okay, there's the pivot point, and there's the moment arm, and that is the torque that is rotating her. Okay, so when she's horizontal like that, that's when the torque is greatest, and when she's right below the suspension point, there's no torque and she won't turn. Okay, so there's her center of gravity. Okay, so for this object, for this object, there's the center of gravity, and there's the pivot point. So if the center of gravity is right below the pivot point, this object will be at rest, it won't rotate. When it's there, this weight will rotate the object in this direction, okay? When the center of gravity is right above the pivot point, you can balance this object. If the center of gravity were to the right of this pivot point, this will just topple over. Okay? And this is what needs to happen if you want to stand. Your center of gravity needs to be within that footprint. You want to fall down, all you have to do is get your center of gravity outside your footprint. Okay? You might want to fall, but your brain doesn't let you fall. Okay? You make compensatory motion. Okay? All right, this thing is called a stable equilibrium position. Okay? When the center of gravity is below the pivot point, this is a stable equilibrium position. Why is that stable? If you disturb it, the forces will bring you back to your equilibrium position. You disturb it this way, it'll bring it back to your stable equilibrium. How about this guy? You disturb it from equilibrium, it falls. It doesn't come back to the equilibrium position. Okay? You move it to the left, it falls this way. Okay? So this is unstable equilibrium. Your center of gravity is above your footprint. You're in unstable equilibrium. Okay? You got to constantly make corrections. Okay? A toddler is not able to make corrections, and they're not able to walk. It takes them 9 months to a year to learn to walk. Okay? All right, so we understand what stable and unstable equilibrium means. Stable equilibrium is when your center of gravity is below the pivot point. Okay?
So on our body, our pivot point is like
Yeah,
the hips between the
no.
the space between our feet.
No, the pivot point is on the ground.
Oh.
Yeah.
Oh, got it. Okay.
All right, so we need to be able to calculate the center of gravity, and again, you don't have to remember all these formulae. So here are two objects. This is the center of gravity. The center of gravity of this object is right there. The center of gravity of this object is right there. The center of gravity of the composite object is the center of gravity of this guy. I'm doing the x coordinate. Is x coordinate times this mass plus x2 times this mass divided by the total mass. Anyway, you'll see that the center of gravity is closer to the heavier object. Yep. So you can calculate the center of gravity of the Earth and the Moon. You can calculate the center of gravity of the Sun and the Earth. So yeah, all right, let me do this, ask you this. So what does the Earth do? What is the Earth moving around? The Sun. Okay. So that's what we're taught, okay? So here's the Sun, here's the Earth. Here's the center of the Sun, and we think that the Earth goes around the Sun. Well, what really is happening is this is the center of gravity of the Earth-Sun system. So in fact, they're both rotating about the center of gravity of that. Okay, so the Sun is also going around that point, and the Earth is going around that center. Okay, so this is about 300 kilometers. So from here to Miami, let's say. Okay, so the Sun is going around in a circle of 300 kilometers. Okay? So you're rotating about the center of gravity. So the whole solar system is rotating about the center of gravity of the solar system. Okay? In fact, so you guys, you guys know about the Doppler effects. When a police siren comes closer to you, the pitch sounds higher, and when it moves away, the pitch is slower. Okay, So when an object is coming towards you, the frequency gets higher, and it happens for light. And when it goes away, the frequency gets lower. Okay, so you guys know about Neptune and Uranus and stuff like that. These planets were far away. And we had a hard time discovering those because it's hard to see these planets. Okay? You need to know exactly where to look at. There's not much light reflected. Okay? So here's the sun, here's Neptune, and this light has to be reflected for you to see. So how do we know? Now you've heard that they've discovered many planets around other stars. We can't even see planets within our solar system. It's a hard thing to do. How the heck do you see planets around other stars that are far, far, far away? Right? Okay, so here's one way. So if a star has a planet, the star has got to move. Remember, they're moving around the center of mass. And now, if the star is moving, the light from it will, just like the Doppler effect, the pitch increases, pitch decreases, pitch increases, pitch decreases. That is easy to detect. So if the light frequency of the planet of the star is changing, then we know it has a planet. So most of the planets, well, so we know that. And now if there's a star like this, if a planet crosses it, when it's crossing, the total amount of light dips, and we can tell. Okay, if the light dips 1 part in 10,000, we can tell. So that's how we've discovered planets. And now the count is about 6,050 or something like that. So we've discovered about 6,000 other planets. Okay, so just to give you a feel, if our solar system were as large as this room, that is, if the sun is here and Neptune is at the other end of the planet, other end of the room, remember we have trouble seeing that guy. And the closest star to us is as far as Miami. You know, how do you see the stars, planets around that? And that's the closest star. You know, there are stars far, far away in South America, and we're able to see the planets around that. Yeah. All right, so here's the center of mass, center of gravity of this guy. All right, so here's a gymnast in a pike position. Okay, so for something to balance, the center of gravity needs to be either above the pivot point or right below the pivot point. Okay, so for this guy to balance like this, see his center of gravity is right above his arms. Is this a stable or an unstable equilibrium? I'm sorry? Very good, unstable equilibrium. Okay, now if so let's say his torso comes forward and the center of gravity tips over, goes like that, goes forward. What he has to do is he's got to move his body back. Okay, so this is a hard position to maintain. Okay, this is okay. So, and if he folds his leg, then this center of gravity will go there, and he'll have to straighten out his legs. Okay. So this is not easy to do. Okay, so he's got to maintain his center of gravity right above his hands. Okay. And this is an unstable equilibrium position. Okay, so this shows you the calculation, how to calculate the position of the center of gravity. You don't have to know this calculation, but I'm just showing you. Okay, so what this diagram shows you is this is the center of gravity of the torso. This is the center of gravity of the leg. Okay, so we model this person as two parts. Okay, and so this is the x coordinate of the center of gravity, meaning how far along the x-axis this is. That's the mass of the trunk, x. Okay, so here's mass of the trunk is 45 kgs, and the center of gravity is at 0. and the mass of the leg is 30 kgs and 20 centimeters. Okay? And that gives you 8 centimeters for that distance. Okay? And similarly, this shows you, this gives you 18 centimeters. Okay? So that's the calculation. Anyway, there are people, you'll need to calculate the center of gravity, but we don't have to do this in this course. On the exam, you don't have to worry about it. Right. You have to be aware of this. See what happened here? There's the center of gravity of this guy. When he stretches, the center of gravity came up. Why did it rise up?
Because his arms weigh something.
Yeah, his arms weighed something, and their distance increased from the floor, and so the center of gravity rose. So just like that, if you stand on tippy toe, your center of gravity will rise. When he bends over like that, you see the center of gravity is outside his body. The center of gravity doesn't have to be within your body. And this is some, so this, and this fella who did high jump back in the day utilized this point. Okay, so took advantage of this point. So, so let's say you're doing a high jump now. I'll show you a side view. Okay, so here's the bar, and here's a jumper that comes up. Okay, and back in the day, they would jump where, so you went sideways and your whole body went over the bar. Okay, so let's say you bent over like this. I'm just drawing. Okay, there's your center of gravity. Okay, so what an athlete can do is lift their center of gravity that distance. And most athletes are sort of equally conditioned, and that's what they can do. Okay, so you can, if you have a certain strength, let's say you can lift your center of gravity 2 meters. Okay, now Mr. Fosbury, remember, he realized that if you bend your body like that, your center of gravity is outside. It's lower than outside your body. So he thought, hey, what if I do the following? What if I put the bar over here, and when I'm going over the bar, I turn my body like that and go over the bar like this. Mr. Fosbury is not any stronger than him, and Mr. Fosbury, he's not stronger than him. But remember what happened. His center of gravity went there, and he lifted his center of gravity the same distance as this guy did, except that he cleared a higher bar. Did you guys understand that? So when you do this Fosbury flop, you see your center of gravity is going below the bar, and you're able to clear a higher distance, a higher bar. Mr. Fosbury did this in the 1968 Mexico Olympics, and he won the gold medal. Okay? And since then, everybody has been doing that. Okay, so you jump like that for pole vault and high jumps. Okay, and your center of gravity is going below the bar. And you see, so again, so these are all the various techniques. In 1896, you did the scissors, and the high jump record was 1.9 meters, which is about 6.4 feet. Even back then, people could jump over the tallest person. And then the Western roll came about. That technique was better, and the record went up. Then the straddle, and that improved the record a little. Once the Fosbury flop came in, suddenly performance improved dramatically. Okay, and now that's the technique that's used. Yep. All right, so again, we'll come back to static equilibrium. That is, an object is at rest and is in equilibrium. And what is it that you want? You want stable equilibrium. Okay. but we are sort of in an unstable equilibrium, except that what saves us is our footprint is fairly large, and it's easy for our brain to make sure that our center of gravity is above our footprint. Okay, let's say if somebody comes and pushes me like that, trying to topple me over, my body will automatically extend my arm. You walked on a sidewalk and you trip on something, you throw your arms and legs away to catch yourself. Okay. Now the conditions are as follows. Okay, so if an object was a point object, the only condition you need for it to be in equilibrium is the sum of the forces be 0. So you see, this force plus this force, they'll cancel each other, they add up to 0. So that's all you need. Okay. Will this, now for an extended object, this condition is not enough. Let's see. Okay. Will this object be in rest? Yes, this force is canceling this force, and this object will be at rest. But now let's apply the same forces like that. Okay, so we apply this force like this and this force like this. These forces add up to 0, but will this object be at rest?
No, it's still gonna turn.
It's going to turn. This is not going to turn, but this is going to turn. So here, the sum of the forces is 0. Here, the sum of the forces is also 0. But this guy is turning. Why is that? Because the sum of the torques is not 0. Okay? This is a clockwise torque. This is also a clockwise torque. Okay? So this was a clockwise torque. This was a counterclockwise torque, and they added up to 0. Okay? So for an extended object to be in equilibrium, you need two conditions. The sum of the torques need to be 0, and the sum of the forces need to be 0. All right, so for an extended object to be in equilibrium, the sum of the forces need to be 0, and the sum of the torques need to be 0. Okay? And like I said, civil engineers do a whole course just based on these two equations. That's a statics course. Okay? So let's see if we can figure this out. Okay. Of these objects, which one will be in static equilibrium, meaning it won't move or rotate?
D.
Okay. So
and B.
okay, B won't be in equilibrium because these two add up to, if these are 5 and 5, 10 pounds, and this is 5 pounds, it'll move in this direction. Okay. D, this is 10, 5 and 5, so that condition is satisfied. Total force is 0, that condition is satisfied. Okay. And in addition, okay, so this is going through the pivot point, so this force has no torque, and this has a clockwise torque, and this has a counterclockwise torque. So for this guy, that condition is also satisfied. Okay, so this is the guy that'll be in static equilibrium. Okay, what is this thing? What is this thing? It's a machine. What does a machine let you do?
More work with less effort.
Okay, so there's no free lunches in life. Okay, so work in is work out. Whatever you put in is what you get out. So what does a machine let you do? Again, work is force times distance.
Allows you to get more work done more efficiently.
No? Okay, what?
Multiplies your work.
I'm sorry?
It multiplies your work.
No, what it does is, okay, if you want to lift a heavy load, let's say, this is the heavy load you want to lift, I'm not that strong. So what I want to use is a device which allows me to apply a smaller force over a larger distance. Okay? So that's what this guy will do. A machine is a force multiplier. Okay? Oftentimes. Other times, can you crack a nut with your bare hands? No. So what does a nutcracker do? It makes you look good. It makes you look stronger. it multiplies the small force you can apply into a larger force to be able to break the nut. And we'll come to that. So for your, so you might be surprised to learn your molars can apply a force twice your body weight. Your molars can apply a force twice your body weight. And we'll see how that is done. Okay. All right. Anyway, let's come back to this. Okay. So here, the man applies a force like this. There's the weight of the bucket, and you see the weight of the bucket is bigger. Okay. Now let me do some numbers. Let's say this is 1 feet, and this is 5 feet. Okay. Let's say it's that machine. So what is happening? This force, there's the pivot point. This force is turning this bar counterclockwise. And this guy is turning the bar clockwise. Okay. And so when the torques balance, this will be at rest, and so he's sort of lifting it. So when he lifts it, it slowly moves. Okay. So the torque, the clockwise torque, remember, is negative, and the counterclockwise torque is positive. So the load, and I'm using different notation, times 1 feet minus counterclockwise torques are positive and clockwise torques are negative. The force the man applies times 5 feet equal to 0. Okay. Now I'll bring this to the other side. So the force that the man applies times 5 equal to load times 1 feet. So the force that the man applies is 1/5 the load. So what this is telling you is if the load is sticking here and you apply a force at 5 times the distance that the load is from the pivot point, if the pivot point is 1 feet, and if you're applying a force 5 feet from the pivot point, your force that you apply is 1/5 the load. So you have to apply a smaller load. That's what, and you've experienced this with a wrench. The longer the handle of the wrench, the smaller the force you apply. Okay. So the mechanical advantage of a machine is the output force divided by the input force. In this example that I showed you, the input force is 1/5 the output force, so the mechanical advantage is 5. Okay? So if the mechanical advantage is 5, that means you're applying a force 1/5 the output force. Okay? So that's what the machine will do. All right.
Output over input.
Output over input. What you're getting for and what you're putting in. Okay? You will see that for, we already talked about this, for your elbow, the mechanical advantage is 0.1. The mechanical advantage for your elbow is 0.1. That is, the output force divided by input force is 0.1. That means the input force is 10 times greater than the output force. You're lifting a bowling ball and you're applying a force. Your tendon had to apply a force that was 10 times the weight of the bowling ball. Bad design. But why did you have to do that? Because your muscles can't compress too much. Okay? And that's why you have to do them. Okay. So the mechanical advantage is the output force divided by the input force. Okay. So again, when your mechanical advantage is less than 1, that's because your input force has to be large. That's because the input distance, that force cannot move too much. Okay. And this is the work you're getting out. And that's the output force times the output distance. Okay. So here's the mechanic. This is the input force, output force. Okay. Okay, now let's come to stability and balance. A tripod or a 3-legged stool is stable just because now it has a larger footprint. Okay. So that's what's done here. Okay, so here's a 3-point stance used by athletes. Okay? So this is a more stable configuration than just standing up like that. Why is that? Because now your base has become bigger. What else has happened?
Your center of gravity is moving.
Bo-
Shifted it to outside your body.
Your center of gravity, well, to be able to balance, your center of gravity has to be right above this footprint. So you've lowered your center of gravity and you've increased your base. That's why this became more stable. Okay? A four-legged quadruped is even more stable. Okay? And that's why babies learn to crawl first. Okay? That's the easiest thing to do. Okay? And your base is much wider. Okay? And a quadruped can easily lift 1 foot off the ground and become a tripod without fear of falling. Okay? So, four-legged animal, the base is stronger, but the base is bigger, and their center of gravity is also lower. Okay, so that's a very stable configuration. Okay, birds, yeah, the stability of a biped is much more challenging because the base of support, the area of the feet plus the area between the feet is small. Okay? So the solution adopted by birds is to have wide feet relative to their body size. Okay? So they have wide feet for stability. Okay? All right, so here is this lady, her center of gravity has to be within that area. Okay, the area of her feet and the area between her feet. Okay, so of course this balancing this is harder than this. It's getting progressively easier. Okay. Humans have relatively small feet. Our stability is due to our brain's ability to constantly adjust our stance no matter what we're doing to keep our center of gravity over the quite small base of support provided. To maintain stability, we unconsciously adjust our position, the positions of our arms and legs. Okay, this is when something upsets our balance, risking a fall, we instinctively thrust out our arms or leg to change the center of gravity. Okay, so we are able to do that, and toddlers are not able to do that, and it takes them a while to learn. Okay, so now this lady, when she stands on tippy toe, what has she done? She's reduced the base. So that's why this position is harder to maintain. Okay, now you got to maintain your center of gravity above this position. Okay, and of course you can't do this for too long. What happened to the center of gravity? The center of gravity, the base became smaller and moved front. The center of gravity rose and moved forward. So now it's a double whammy. Your center of gravity rose. Lower the center of gravity, the more stable you are. It rose, and then it has to be balanced over a smaller area. I guess very hard to maintain. Here's another example. So this is gymnast. There's her center of gravity right above her arms. Now if her body moves forward, she would have to stretch her leg to bring the center of gravity back. Okay? And if she toppled over this way, she'll have to move her body this way or move this leg that way. Okay? This is a very hard position to maintain. So the gravitational torque on our extended legs offset the gravitational torque. It takes long practice to learn to perform this. Okay? So the gymnast's center of gravity needs to be maintained right above her arms. Is this a stable or unstable equilibrium? Unstable. So here are three objects. Those are their center of gravities. Which object is the most stable? Okay, so here's how stability is defined. So if you're an object, or you can think of it like so. If here's an object, to topple it over, how much do you have to tilt it? Okay. The greater the so this was the vertical position. Okay. The greater the angle you have to tilt, the more stable you are. Okay. Okay. So for stability, what you want is the lower the center of gravity, the more you would have to tilt it. So this is the most stable. Okay? And between these two guys, if the center of gravity were at the same location, this has a greater base, this would be more stable. But the center of gravity is higher, so you have to calculate based on that. Okay? So this is the most stable. Okay? Again, the lower your center of gravity, the more stable you are. Okay? All right, guys, we're going to stop here today.